as I talked earlier, we're going to talk a little bit about the wildfire smoke and kind of some things we've been learning on this front in terms of how it impacts the crops, both positively, negatively. I also am going to sneak in a little bit on heat. So one other topic of concern is just heat stress in general. Heat stress impacts, so we're going to talk about that here coming up as well. I do want to share this, from the fact that myself and a lot of the other Midwest corn agronomists all across the U.S., we kind of came together in the last year or two and decided there's a lot of information out there in terms of how do different environmental factors impact corn, but we want to try and really understand them and summarize them. So, we do scientific articles and stuff like that. This is one of my favorites because there's a lot of pictures and it's a lot easier to read than a lot of the other scientific manuscripts we write. It's also free to download. So it's a nice article. We published 2 of these. They just give you a good summary from everything from drought conditions to flood conditions to hail to root damage to all these different weather. We did long-term weather stresses, short-term weather stresses, and how they impact corn. So some of the information I'll present today is explained in a little more detail in a couple of these articles. So I did want to share that out because they just came out this year and just last year. So they're pretty fresh and just summarizing all the information that's been done and what's out there in terms of environmental impacts on corn. So I share this graph right here. So this is data that I took from both the Canadian and the U.S. National Forestry database in terms of what are the total acres burned by wildfires. So Canada is on the left. Canada data goes from 2000 to 2021. And then on the right-hand side is the U.S. data. U.S. data goes from 1983 to 2022. So you can see a fairly clear trend both in the U.S. and Canada that line is increasing. This is something we've noticed in both countries, that the amount of acres burned by wildfires has steadily been increasing, and the fact that 2023 was a record for Canada in terms of total acres burned by wildfires. That's probably why a lot of people noticed it. A lot of people were asking about its impacts really across the entire Midwest. I gave a talk out in Iowa last year, and this is what they wanted to talk about. This is what they wanted me to talk about because they saw a lot of those impacts all the way out in Iowa last year. But just showing you, hey, from the data, they track all this, that those total acres burned by wildfires are increasing over the last 20, 30 years. This is just a U.S. map. Gives you an idea of, okay, wildfires are increasing. Where are they increasing? In the U.S., it's predominantly on the east or the west coast. So California, Washington, Oregon, on the bottom there. So the darker red that you have is the more of an increase in square miles of landscape that were burned by wildfires. And this is the difference between 1984 to 2000 and then 2000 to 2020. So two different 20-year periods. You can see over the most recent 20 years, particularly in the West Coast, some in Oklahoma, down into Texas, but predominantly on that West Coast is where we're seeing this overall increase in wildfires occurring in the U.S. So it kind of gives you an idea of where a lot of these wildfires are occurring predominantly in the U.S. and how much it's increasing. So why are wildfires increasing? I think there's a lot of different factors with this and trying to understand this. One of the big reasons is, at least from a U.S. side, has just been the changes in forest management. Previously, they went away from a lot of the prescribed burns. So typically, in the past, when they had prescribed burns, they would, obviously prescription burns, targeted burns, controlled burns to control a lot of the kindling and issues and the fuel loads in these forests. So they've changed a lot of that. They went away from it. Now they're trying to get back to that. The challenge with it now is that, one, they have to have certain conditions on certain days in order to do these prescribed burns. They have less and less in those days. So this graph right here, what it's showing, those lines are different areas and the number of days that they designate, hey, this day is adequate for us to do a prescribed burn. But one, the number of days that they can do the prescribed burns is getting less. The other one is that cities are expanding. Cities are expanding in a lot of these areas in the West Coast than what they were 30, 40 years ago. So it's getting more and more challenging to do these prescribed burns because you're closer to people as well. So it's kind of a twofold aspect that, we saw a reduction in prescribed burns, the fuel load increased, and then now we're trying to go back to that, but it's getting more and more challenging to be able to do these prescribed burns, which results in increased fuel load, and then also that potential with the overall, igniting of these wildfires. Another aspect is just changes in climate, right? The weather is changing. One of those is temperature. One of those are just increased periods of intense drought. So you look at the intensity of drought conditions where you might have a 2-3 week period or a month period where it gets really hot and really dry. Those are becoming more and more common, so that can ignite the overall fire. But we're seeing increases in temperatures, increases in periods of dryness, and then just increased periods of that intensity of both the dryness and that high temperature. So this is some data from the National Oceanic and Atmospheric Association from the US. You can see from about 1980 till now, 2020, the Earth's surface temperature is increasing. This is something we know, hey, the temperature is increasing. This is just a factor that when we have temperatures increasing in a lot of these areas and the intensity of that temperature increasing, that's also going to result in igniting of a lot of those fires. So that's a factor that is also impacting the overall wildfire predominance across the U.S. Another piece of that is not only the heat, but also lack of precipitation in some of these areas. So you see big swings in terms of, hey, it's getting really hot, but it's also combined with times where it's getting really, really dry. So this data right here, all I want you to look at is the lower right-hand quadrant of this data. The lower right-hand quadrant of this data are where we have years where the temperature is above normal, so deviation from normal, and then the precipitation is deviated below normal. So the proximity of the years, you look at those dots in the lower right-hand quadrant, what do they correspond to? The dots that are highlighted. Where are the majority of the dots that are highlighted at? In that lower right-hand quadrant. That means years where we have below average precipitation and we have above average temperature. Those are the worst wildfire years that we've had in the past. So it makes sense. So years where we see higher or lower amounts of precipitation, higher temperatures, we're seeing more incidences of wildfires. And then you look at the years, right? The worst fire years are the red dots. That's, fairly recent, 2020, 2007, 2018, 2008. So more recent years where we're seeing, a deviation and drop of precipitation and increase in overall temperature resulting in that. So this is what we saw in 2023. These were some images taken from NASA that I pulled from their website. And they're using their different tools where they actually looked and tracked where the smoke was going. We had a lot of both Western Canadian fires and then parts of Eastern Canada as well. You can see the image on the right. That's just black carbon in the air. So you can see, where the intensity of these fires were, but how much it traveled. It traveled a long ways. It dipped all the way into the Midwest. You can see even parts of, if you look close enough, Ontario there, and then even dipped into Indiana, but even parts of Iowa, Nebraska, the Corn Belt just saw a lot of this black smoke, a lot of this, blocked out sunlight and just smoke in the air last year. But it's really interesting to see, far northwest Canada and far northeast Canada, we're having these wildfires. That smoke is dipping all the way down into these high crop production areas. So that became the question of, okay, what is it doing to the crop? We see it. Some people told me they could taste it out in that field. So what is it doing to these crops? And right here is a picture that I took. This is, I think, June 23rd in West Lafayette, Indiana, near campus. And this is from a UAV image. Can you tell it looks a little hazy there in this image? This was probably the worst day that we had for wildfire smoke. This is one of our research trials. You can see we had different nitrogen treatments and different hybrids and aspects like that. And this trial is a field scale trial. But I thought the image was really interesting because you could really tell that wildfire smoke was in the air on that day. And you could really see it from this image. So it was June 27th, kind of that last week of June. Last year is where we had a lot of the issues that we had across the Midwest. So the question we have is, are these conditions impacting Midwest corn production. And I'm going to give you the most political extension answer that I could possibly come up with. Yes and no, and it's complicated. All right, I'm done. Thank you. But it's challenging, right? And that's what we're going to go through. So some folks may think, well, it's all bad or it's all good, but there's different aspects of it. But the big thing is it can positively impact corn, it can negatively impact corn, and it is complicated and it's difficult to try and understand. But we're going to try to, right? We'll try to here coming up. So we'll go through some of the negative aspects of wildfire smoke. First one is probably the first one you think of with wildfire smoke, is it reduces sunlight. So it reduces, reductions in sunlight. It actually reflects sunlight. So the particles in the air from the wildfire smoke can actually reflect that sunlight. And when it reflects the sunlight, it's just reducing how much sunlight is getting down to the crop. When we reduce the overall sunlight, if you know, plants need sunlight to photosynthesize. If we reduce that overall sunlight, it's going to impact the overall photosynthesis, and it's going to reduce some of that photosynthesis. Another kind of negative aspect of this, and one that you probably don't often see, it has to be pretty intense in terms of what that wildfire smoke is, but it actually increases ground level ozone. And increased ground level ozone, one, can be harmful for humans and animals. So one thing we noticed, and probably you noticed during these wildfire smokes, you might have had air quality warnings. Air quality warnings, and you're breathing this air. So it can increase ground level ozone, which can be toxic for humans and animals, but also can impact plants. So it can impact plants, particularly during respiration. So where that plant will take it in and that can actually burn some of that tissue. This is something we don't always see, but it can happen when you have really high levels of wildfire smoke. So here's some data out of Iowa. Mark Jeschke is one of the main head agronomists with Corteva and Pioneer. And he did a lot of work diving into some of this in terms of, if we have cloudy days, right? We have cloudy days, we reduce sunlight, how much is that reducing photosynthesis in the crops? So one thing we did notice is that he tracked full sun on the left-hand side. He looked at partly cloudy days, and then he looked at cloudy days, and then he looked at rain. So this is just looking at daily light integral or overall sunlight. So if you have, say, a full sun, not a cloud in the sky day, and then you move to cloudy, like a day like today, earlier today we had mostly cloudy, that's about a 50% reduction in overall sunlight. So that's quite a bit of a reduction in sunlight. You get over to rainy days, that's about 60+% reduction in sunlight. So that could track to reductions in overall photosynthesis. This is some data from Ohio. The big thing that they looked at is just 2017 through 2021. They had some wildfire smoke in 2022. In June and July, they saw about a 7% and 6% overall reduction in sunlight. So the big thing is that, hey, when you have wildfire smoke, it's probably going to reflect some of that sunlight. It's probably going to reduce some of that sunlight that we see. And that could potentially negatively impact that crop. So this is some data that I pulled from northern Indiana. We actually look at solar radiation. We have weather stations and sensors all over that track solar radiation. So this is radiated flux, solar radiation. And this is during that time period of that picture that I showed you. So right in that last week of July, or last week of June, you can see we start June 24th on the left-hand side, but I had highlighted with the arrow there that you can see that pretty strong dip in the reduction in solar radiation and the reduction of sunlight. So you see that dip when that wildfire smoke comes in, and then it kind of picks back up. But did want to highlight that even with our sensor, we're able to pick up a pretty strong reduction in overall solar radiation when that wildfire smoke did come through in the later half of June last year. In West Lafayette, Indiana, total solar radiation was reduced by 32% in the week of June 26th in comparison to that week prior. So I just looked at the data across that entire week, compared it to the week prior. It was about a 32% reduction than the week prior. So why is that a problem? Why is that maybe more of a problem than corn? So I always ask people, if I have a reduction in sunlight, is it going to impact corn or soybeans more? Anybody know? Anybody do you think corn will be impacted by reductions in light? Raise your hand. More? Probably more hands. Or soybeans? Anybody think soybeans will be impacted by light more? It's actually corn. So why is that? Corn is a C4 plant. Soybeans are a C3 plant. It's just a way when you think about the photosynthetic pathway of that plant. But the big reason why is this graph here. And the reason why is that corn has a higher light saturation point than soybean has. And what I mean by that is that means it takes more sunlight for a corn plant to reach maximum photosynthesis than it does soybeans. So if you look at the dotted line, that is leaf photosynthesis versus irradiance or sunlight on the x-axis. It takes more sunlight in order to reach that maximum photosynthesis in corn than soybeans. Soybeans are going to reach their maximum photosynthesis at a lower level of sunlight. So corn is actually more sensitive to reductions in sunlight than soybeans are. It has a little higher light saturation point. Soybeans, C3 plant, they're actually more sensitive to changes in CO2. So soybeans are going to be impacted more with changes in CO2 than corn. Corn are going to be impacted more by changes in light. So keep that in mind that, hey, if we see reductions in sunlight, it's probably going to impact corn maybe a little bit more than it will impact soybeans. So the challenge with this is just studying it. How do you have one simulate wildfire smoke and then try and get an estimate of, okay, it's reducing sunlight, but how much is it reducing yield? And that's really challenging, and the way they've kind of done this in the past is just use shade treatment. And now in my opinion, that's kind of too extreme, right? When you're really shading out that crop and you're doing it for a long period of time, but it can kind of give us an estimate of, okay, if we do reduce some of that sunlight, and maybe if it's a little bit extreme, how much does that reduce yield? So here's a study from 2019. They saw a greater than 50% reduction in overall yield when they reduced solar radiation by 50%, but extended that from silking to maturity. So predominantly through grain fill, if you reduce solar radiation that whole time by 50%, yield was lost greater than 50%. So it can have a pretty big impact in yield if it's sustained for a while. Another study, this is from the early 90s, but they looked at reductions in solar radiation of 50% for about 44 days after emergence, all the way to maturity, so a longer period of time. Okay, we're reducing yield all the way up to 66%. So seeing big reductions in yield. And then lastly, this study in 2009, they looked at, okay, reduced solar radiation for like 2-week periods during the vegetative growth, reductions in yield 3%. Go to tassel silking, a couple-week period at that point in time, 12%. And then we're getting into post-silking, so just after tassel, about 21% reduction. So the idea of this is just from the fact that it kind of depends on, one, the duration of sunlight being reduced, and also depends on when that sunlight is being reduced. If it's being reduced in vegetative growth for maybe only 1 week or 2 weeks, it's probably not going to have a big impact on yield. If it's during tassel for maybe 2-3 weeks during tassel, or just after tassel, it's probably going to have a much bigger impact on yield. So I talked about the negative impacts, but there's positive impacts. So smoke can actually have positive impacts on that crop. So why is that? One is what we call a very fancy word called diffuse photosynthetically active radiation. And all that I mean by that is that I talked about smoke can reflect light, it can also scatter light. And when it scatters light, when light is scattered, it actually can penetrate into vegetative canopy better. So they've done a lot of this work out in California and the West Coast and in different areas where they have wildfire smoke, and they see that this PAR, this diffuse photosynthetic active radiation, increases, which is just a fancy word for scattered light. It actually, instead of reflecting it, it scatters it. It also redistributes that sunlight a lot more and can penetrate more into the canopy. So we see greater light use efficiency. We also see higher photosynthetic efficiency from that crop when we have some of that wildfire smoke. And when you have a crop like corn, that's C4, a little bit more sensitive to light, and has a multi-layer canopy, like corn does, you have a lot of different leaves and different layers, that if we are able to redistribute that light and penetrate that canopy better, it's going to have more of an influence on that crop. And probably one of the biggest pieces in what we saw last year. So I tend to lean towards maybe that wildfire smoke helped us out a little bit last year with corn. It was leaf surface temperature. In late June, in a lot of areas, one, we were dry, but we were hot at that point in time. And when you think about if we're able to, one, reduce the overall sunlight, what does that do to temperature? Reduces temperature. It's going to reduce the surface temperature on those leaves, and it's going to reduce transpiration or water loss from those plants. So we had leaves rolling in our crop at that point in time in late June. When that wildfire smoke came through, you almost could feel or hear the plant give a breather, right? They just breathed a little bit. We saw less rolling. We had indications that the transpiration on that plant was reduced, water loss was reduced, and the overall stress of that crop is reduced. And that's often a function of when it comes in. When does the wildfire comes in? Because if this happens now or when you're getting closer to harvest, it can also delay that crop as well in terms of maturity and overall harvest time. So just looking at this data, just look at the relationship between the top graph. The top graph would be your solar radiation. You can see the bars start to decrease. The bottom graph is temperature. So this is the same time period. We're looking at temperature. We're going from, I think this is June 21st temperature on the bottom all the way to June 27th last year in West Lafayette. June 21st, we had a high of about 88 degrees. You look at June 27th, we had a high of 70 degrees. And that's when that wildfire smoke came through. A difference of about 15, almost 20 degrees in that overall air temperature when it came through. So that crop, in terms of transpiration, leaf surface temperature, and water loss, that crop kind of had a breather there when we were pretty hot and pretty dry at that point in time. And why is that important? Because it came during vegetative growth for the corn crop in the Midwest. And again, we were hot and we were dry. This graph shows a lot of the corn belt. The more yellow and darker orange that you are, the amount of reduction in average precipitation that we had. So West Lafayette last year, I think we had 0.95 inches of rain in the month of June. That is very, very dry for the entire month. So the fact that wildfire smoke could come in, reduce some of that leaf transpiration, reduce some of the stress on that crop, potentially helped it during that period of time. And here's some data to just kind of back that up. Where we have air temperature on the left-hand side, we have transpiration rate, which is just the amount of water being lost from that plant, and then they have net photosynthetic rate on the right. So if you go from 77 to 86 degrees up to 95 or 104 degrees, that transpiration rate can drastically increase. In some cases, almost double the amount of water that's being lost from that plant, and the photosynthetic rate or the net photosynthetic rate goes down. So that plant is losing more water, it's working harder, and its photosynthesis is going down. So if we're able to lower that temperature, maybe have some scattering of that sunlight, we're able to increase, one, the photosynthetic rate, and reduce some of the transpiration and the amount of water loss from that plant. So this is, again, just jump right into heat stress. So another topic is just overall heat stress, why that is. Temperatures are increasing. This is from 1895 all the way to 2023. This is the U.S., continental U.S. You look at the temperatures, they are increasing. We're just having more hot days out there, so more of a risk of potential heat stress in corn. So how does the heat stress impact that corn crop? We just talked about this transpiration rate, the amount of water loss that we've had. So the state of Indiana, the last couple weeks and across the Midwest, it's been hot, very, very hot. Mid-90s up to almost 100 degrees in certain areas. And if you ever heard of corn sweat, when it gets really hot this time of year and the humidity, the dew points in localized areas where you have a lot of corn goes up. If you just Google corn sweat, I've gotten some calls on this, where they find towns and localized areas where the humidity and dew point goes up because of the corn crop. So what we find is that when you have heat stress and we have these hot weather comes through, the transpiration rate or the amount of water loss from the crop goes up. There's more water in the air, it can actually increase the overall humidity in these really high crop production areas. So how does heat stress impact corn? Transpiration rates, more water loss, photosynthetic rates, we saw this previously, those can go down. Respiration rates, I talked about this a little bit in the demo where you have high nighttime temperatures. That crop's just gonna work a little bit harder. We saw this a lot across the Midwest last week, where it was like a flip of a switch. That corn plant started shutting down because of how hot it got. That crop was just working harder, predominantly at night, when it's doing a lot of its work at that point in time. Respiration, you have high nighttime temperatures, and that crop's working harder. It's going to burn a lot more energy and potentially shut down a little bit earlier. Pollen viability is another one. We'll talk about this. It can desiccate pollen if you have really high levels of heat. Silk desiccation is another one. You have really low humidity and high heat at tassel, one that can throw off the synchrony of pollen drop to the silks, but it can actually desiccate the silks. Silks are very sensitive. They're very sensitive, and they also have high water content. So any form of stress, largely drought, but also heat stress, when you have really low humidities and high temperatures, can desiccate that silk. But the challenge with differentiating, hey, the heat caused this issue of that corn crop, is that it's often layered with drought stress in corn. So differentiating those two can be pretty challenging. So this is just a graph that shows leaf photosynthetic rate by temperature. So you look at corn crop C4, which is that dotted line. As the temperature goes up, this is in Celsius, you can see the overall leaf photosynthetic rate of corn. When it gets to be about 30 degrees Celsius, it's peaking. You get above that, look at that leaf photosynthetic rate after it hits that peak, it goes down, right? So the higher that temperature goes, that crop, one, is still growing, but eventually it's going to reach a point where that photosynthetic rate starts to really drop off as that temperature continues to increase. So corn, C4 plant, net photosynthetic rate begins to decrease at 86 degrees Fahrenheit. Have you ever heard us talk about growing degree days, modified growing degree days, where you have a 50 degree bottom and an 86 degree top when we calculate growing degree days? Why do we use 86 degrees as our top? Right there. So leaf photosynthetic rates of that crop starts to really drop off when you're above that 86 degree Fahrenheit or 30 degrees Celsius. Soybeans do have a little bit higher tolerance to higher temperatures, corn has higher tolerances to higher temperatures than soybeans do. C4 crop, tropical grass, corn can tolerate pretty high temperatures in short bursts. It's when they're sustained for a longer period of time when it's impacted. And this is mostly a problem during those critical growth stages. Tassel in corn is super sensitive at that point in time. Why? Because it's at peak biomass, it's at peak water use, a lot of peak nutrient uptake. It's just a machine at that point in time. But corn is super sensitive. I always say if you look at a corn plant wrong at tassel, you could potentially lose yield because it's sensitive. So that's why when you think about drought stress and heat stress, when are we going to see the largest reductions in yield? It's going to happen at those reproductive growth stages. So can high heat kill pollen? Yes, it can kill pollen. So when you have greater than 90 degrees Fahrenheit, you see a little bit of a reduction in pollen germination. When you get to higher than 95 degrees Fahrenheit when corn is pollinating, we do see one depression in pollen production. We start seeing that silk desiccation. And then when you get higher than 100 degrees, we can see pollen death. It's probably in this part of the world, and part of Canada and up into Michigan, right? We don't often see this, but doesn't mean it can't happen. When you have 100 degrees in mid to late July when that corn plant is pollinating, but it can desiccate or kill that pollen, desiccate the silks and kill that pollen, or drastically reduce the viability of that pollen. However, this is very rare in the Midwest. Even if it happens during the day, if we had 100 degrees at 2-3 o'clock in the afternoon, anybody have any ideas on maybe why this is rare that this ever happens? Any ideas? It's this graph right here. It's about the pollination timing for corn. So when does corn do a lot of its pollen drop? In the mornings. It likes to drop a lot of its pollen in the morning. So this graph, this is from a study published in 2010, but on the y-axis we have rate of pollen shed. I would not want to be the researchers that did this kind of work, but they did it. They measured pollen shed, counted pollen grains, and they looked at the time of day. And I think that's 2 different hybrids is what they looked at there. Or no, 2 different years, so 2 different years. And really what they found is that the corn does a lot of its pollen drop at about 8 to 10 in the morning. So early in the morning, during that period of time is when you're going to see the largest rate of shed and the largest pollen drop during that period of time. And then it really tapers off as you get into the heat of the day. So you think about if we get those really high temperatures, they occur at say 2, 3 o'clock in the afternoon, it's probably not going to impact that crop a whole lot because it did a lot of its pollen shed early in the morning. So this is the case on why a lot of areas with high corn production, we just don't see much of an issue from any pollen desiccation or reductions in pollen viability because of when that corn plant actually sheds pollen, when it's a lot cooler in that morning. So another aspect and another thing that we've looked at is just, okay, what about vapor pressure deficit? And I talk about vapor pressure deficit, and that just kind of combines both humidity and it combines temperature. So when you have temperature, when you have higher temperatures, it takes a higher amount of moisture in the air to reach saturation. That vapor pressure deficit, as it goes down, is often a function of higher temperature. Higher temperature, higher vapor pressure deficit. So that deficit is bigger. That results in higher transpiration, more water loss from that crop. So corn responds to higher vapor pressure deficit by closing its stomata. Have you ever seen a drought-stressed corn plant out in the field, or even a heat and drought-stressed corn plant? It rolls its leaves. So one of the biggest reasons a corn plant rolls its leaves when it's stressed from both drought and heat is that it's one, closing its stomata, so the little holes on where you have that transpiration release of that water loss from the plant. It's going to reduce how much water is being lost from that plant, and it's also protecting those leaves from being exposed to that sunlight and reducing some of that surface leaf temperature. So corn plants, one of the most common symptoms you'll see when it gets really hot and dry out there is rolling leaves, and that's just a defense mechanism. But if a corn plant does that for a long period of time, it can start reducing yield. And really drought-stressed, severe plants, they actually start to turn gray. You've ever seen that? In 2012, we saw that with the drought. And that's just that plant closed its stomata and rolled its leaves for so long that it was not taking in CO2, and the photosynthesis was being reduced. So another piece of that is a lot of combination of both temperature and overall humidity, and then the amount of water loss being from those plants. So just looking at this graph, just look at the left 2 figures versus the right 2 figures. So that's the main thing. You don't have to worry about the numbers or the data there. This is just looking at total water loss from corn plants, transpiration rate, how much water is being lost. On the left two sides are 77 degrees Fahrenheit. On the right 2 sides, 86 degrees Fahrenheit. So if we have higher temperatures, what do we notice? The lines on the right-hand side are higher, and they keep going up higher. That just means when I have higher temperatures at this point in time, transpiration rates are going up. Water loss from the plants are also going up. So to wrap up here with overall take home in terms of heat stress, right? So heat stress can be similar to wildfire smoke in the fact that it's very complex. It's very complex to understand and kind of isolate out how does heat impact that crop, because it's often kind of overlaid with drought stress. Typically when we have really high temperatures, we're always having drought conditions. Corn can tolerate really high temperatures when it has adequate soil moisture. But there's a period of time where if we have sustained really high temperatures, it can impact that overall crop. Like anything we do in agronomics and managing crops is that timing is super critical. Right? I always talk about that you have to manage that crop throughout the entire year. It's developing yield throughout the entire year. But corn can tolerate different stresses better or worse depending on when it happens. So the timing is really, really important on 1, when does the heat stress occur, or 2, when does the wildfire smoke occur. So anything that impacts net photosynthesis, anything that impacts that crop during pollination typically always tracks to higher reductions in overall yield because of how sensitive that crop is at that point in time. Photosynthetic reductions and elevated transpiration are likely bigger impacts. Pollen shed, we talk about, yes, can heat stress desiccate silks, and can it drastically reduce pollen viability? Yes, it can. The aspect is that corn, one, pollinates in the morning, and it doesn't only pollinate on one day. It's a short period of time, about 7 to 10 days. But corn pollinates in the morning, and it can pollinate for 7 to 10 days. So typically, it gets enough pollen and produces enough pollen, one at cooler temperatures and over a period of time, where the lack of potential of that really heat stress and impacting that pollen is drastically reduced. So to wrap home with wildfire smoke, this depends on where I give this talk. You can blame California. I crossed out Canada. Depends on where I give this talk, if I say this. So, cross out Canada is not Canada's fault last year. You can blame California. A lot of Midwest farmers love blaming California for things. So that's why I add this in there. I crossed out Canada because obviously where we're at, right? So blame California. That's where, the West Coast, right? That's where a lot of, changes in management and where these wildfire smokes are. Yeah, so the West Coast, very different than the Midwest and the U.S. You can see that's where a lot of the wildfire smoke is. So that's my first point. If you needed something to add to your Blame California list, there you go. Understanding how wildfire smokes impact crop yields are very complicated. Right? And I talked about this earlier, that why is it complicated? Because one, it can impact the crop negatively, and two, it can impact the crop positively. And I would say last year I tend to lean more towards positively. You think about the reductions in transpiration rates and leaf surface temperature, the outstanding yields that we had in a lot of these states. I went up to Saskatchewan and gave this talk up in Winnipeg and parts of more western Canada, northern western Canada last year. And every single one of those farmers up there told me how outstanding their crop was, how good their canola was in those certain areas. And they had really bad wildfire smoke. So I tend to lean towards, hey, it may have helped some of these crops. We think the way it can diffuse that sunlight, scatter that sunlight, maybe reduce those temperatures. Now, do we need wildfires all the time so we have great crops? Probably not, right? But just showing you, hey, that there's both positive and negative impacts, and that's what makes it pretty complicated to try and understand how it impacts that crop. They've done a little bit of work in this as well, predominantly with shading, but hybrids. They've done some work with, just overall shade cloth and looking at reductions in sunlight. Hybrids differ in the way they respond. They found that different hybrids do better in terms of their tolerances and overall reductions in sunlight. Also at plant populations, you think about a lower population versus a higher population. And you think about the amount of competition between plants. If we see a reduction in sunlight, probably a higher population area is probably going to be impacted more than a lower population area in terms of seeding rates and populations per area. And then again, like everything we do, we just need more research in this area, because we typically use shade reductions and shade cloth studies and sunlight reduction studies as proxies to try and understand, okay, if we reduce sunlight, here's the negative impacts. But how do we also quantify maybe some of those positive impacts as well? That's really, really difficult to try and study. I haven't found a good way for Purdue to let me, stoke fires out of their farm and capture that smoke to look at some of this research. If any of you come up with a better idea for that research, let me know. So as I wrap up here, I'm happy to take any questions. I did want to share my information. I wasn't able to do this when I was out in the demo plots, but I want to share my email, share my phone number, and then also share my website. So my website is thekernel.info. It's a shorter URL. I also have a long Purdue URL, but this URL will get you to the same spot. I talked a little bit about our research and what we do. I do about 50 research trials across the state of Indiana that range from northeast Indiana down to southwest Indiana. We span a lot of different topics. I work with equipment, I work with fungicides, I work with biologicals, I work with hybrids, I work with planters, a lot of different things. And our research book, so we have a book that we've been slowly starting to publish. The digital copy is on the front page of that website. So I want to make sure that's available. Log on the website, you can see there's a link straight to that kind of digital copy that's just sharing a lot of the yield results from a lot of these trials that we do. We do a lot of product evaluation, hybrid evaluation, a lot of different trials in very diverse environments. So I did want to share that website so you can access some of that information as well. If you're on social media, which I'm sure you all are avid users of social media, Purdue Corn there, and then myself and Mo mentioned Sean Castile. So Sean Castile is our soybean agronomist. We do a lot together. We bounce ideas off each other and give each other a hard time as well. But we have a podcast that we do about every 2 weeks, just giving you an update on what's going on in terms of what we're doing, what we're seeing in Indiana. So if you're ever curious about what's going on in the state of Indiana, all the way up here in Ontario, feel free to tune in with that podcast.